Okay, so we're continuing our discussion of the ideal gas law, and we're working our way up to solving some problems using the ideal gas law. And before we get there, we need to talk about STP, standard temperature and pressure. So when dealing with some of these ideal gas law problems, it's common to establish that the conditions are at STP, standard temperature and pressure. So what does that mean? Well, first of all, the standard temperature is 273 Kelvin. So we need to remember that when dealing with the ideal gas law, it's based on Kelvin. So the temperature should always be in Kelvin. The standard pressure, the standard average atmospheric pressure is 1 atm. So that's 1 unit of pressure. That corresponds to 1.013 times 10 to the fifth newtons per meter squared, which converts to 101.3 kilopascals. An interesting thing about gases, or ideal gases, is that if you have a mole of an ideal gas, so you have a mole of, let's say, hydrogen atoms, they will occupy 22.4 liters. And so it doesn't really matter what the gas is, what the atomic weight of the molecules is, for instance. If you have a mole of them, that's how much volume they take up. So that's an important thing to remember. A mole of an ideal gas is 22.4 liters. And then if we're talking about, if the problem statement involves a fixed number of molecules, so we're not gaining additional gas or losing any gas, it's a closed system, then we've got the PV equals nRT. If this stays constant and doesn't change, then we can take the T over to the other side of the equation. We get PV over T equals nR. R is always a constant. It's the ideal gas constant. And if we're saying that N is constant as well, that means the entire right side of this equation is constant. So although the pressure may change from P1 to P2, and the volume may change from V1 to V2, and the temperature may change, the relationship between these three variables will remain constant. So PV over T for condition 1 equals PV over T for condition 2. So this is basically just a simplification or another way of using the ideal gas law when we assume that it's a closed system, that no molecules are getting in or out. So again, just remember T should always be in Kelvin, and P is the absolute pressure. Don't forget that like when you measure the pressure in your car tire, that's just the gauge pressure. You also need to add to that the atmospheric pressure to get the absolute pressure. This slide is a bit of a review of what we've already talked about. We've already said how a mole is just a really big number, and specifically it's Avogadro's number. So 6.02 times 10 to the 23rd is Avogadro's number. It's a big number. It's a mole. So if you have a mole of something, if you have a mole of moles, you would have 6.02 times 10 to the 23rd moles. So n sub a is Avogadro's number. This little n is basically saying how many moles. And this n sub a is 6.02 times 10 to the 23rd. Oh, I left off the 2 here, so let's make that 23rd. So the total number n of something is just how many moles multiplied by 6.02 times 10 to the 23rd. So if we were wanting to know how many carbon atoms we had, if we had 3 moles, it would just be 3 times 6.02 times 10 to the 23rd would equal 3 moles. And that would be 1.806 times 10 to the 24th. So that would be, so N would equal N times NA, or 3 times NA, if we're talking about 3 moles of something, which would equal 1.806 times 10 to the 24th. This is a slightly different way of writing the ideal gas law. Rather than PV equals nRT, we can write as PV equals big N times KT. So that introduces a new variable, K. K is called Boltzmann's constant. And we'll talk more about Boltzmann a little bit later. But Boltzmann's constant is equal to R, the ideal gas constant, which we introduced earlier in its 3 different forms using different units. In this case, we're using the 8.314 joules per mole Kelvin divided by N sub A, the Avogadro's number, 6.02 times 10 to the 23rd. So this is Boltzmann's constant, 1.38 times 10 to the negative 23rd joules per Kelvin. So we can plug that in here and use N, the total number of molecules or atoms, rather than the little n, which would normally represent the number of moles. So slight variation, basically the same equation. Let's look at an example problem now using the ideal gas law. So we have a helium party balloon that's assumed to be a perfect sphere with a radius of 18 centimeters. It's at room temperature, 20 degrees Celsius, and the internal pressure is slightly greater than the external pressure. We can assume the external pressure is 1 atm, and the internal pressure is 1.05 atm. So let's find the number of moles of helium. How many individual molecules of helium are there inside the balloon? And once we know that, what is the mass of the helium needed to inflate the balloon to these values? So first of all, we need to calculate the volume of our balloon. Now, not all party balloons are perfect spheres, but this one is. So the volume can be calculated at 4/3 pi r cubed. So the radius was given to us in centimeters, I believe. Let's take a look at that. Yeah, radius of 18 centimeters. So we want our volume to be in cubic meters. So we need to take that 18 centimeters and move that decimal place 2 places to get, I'm sorry, not there, but here. I can fix that. Got my eraser tool. I can erase that decimal point. Don't want that one. There we go. So 0.18 meters. 0.18 meters cubed times 4/3 pi gives us this volume in cubic meters. There's our volume. I'll do this conversion on the next slide, but 1 atmosphere is equal to 1.013 times 10 to the 5th newtons per meter squared. And 20 degrees Celsius, that's our room temperature, but we need that in Kelvin, so we need to add 273 to it to get our temperature 293 Kelvin. That's our temperature. And then R is a constant. We were given in a previous slide 3 different versions of it. We want this one, the 8.314 joules per mole Kelvin. Why do we want joules? Well, because we're using our standard units of newtons and meters, and a joule is a newton meter, so that is going to be consistent with our other units. So like I said, we need to convert that or find that pressure. The pressure inside the balloon was 1.05 atmospheres. So we need to multiply that by our conversion factor of 1.013 times 10 to the fifth. That's how many newtons per square meter there are for every 1 atmosphere. We multiply that out and we find that the internal pressure in the balloon is 1.064 times 10 to the fifth newtons per square meter. So now that we've got the pressure, that's P, and on the previous slide we had volume and temperature, we can now use the ideal gas law. So the ideal gas law is PV equals nRT. And we want to know N. We want to know how many molecules there are inside this balloon. So N is going to be equal to PV divided by RT. So the pressure is 1.064 times 10 to the fifth newtons per square meter. The volume was 0.244 cubic meters. R is a constant, and that is 8.314 joules, or I can write a joule as a Newton meter per mole Kelvin. And the temperature has to be in Kelvin. That's 293 Kelvin. So the 2 kelvins will cancel out. The square meters here will cancel out 2 of these, so that cubic meters becomes meter. Since we're dividing by Newton meters, the Newton on top gets canceled out by that. That meter gets canceled out by that. And I'm left with 1 over moles on the bottom. When that gets flipped up to the top of the equation, it just becomes meters, or I'm sorry, moles. So our number of moles, all the units cancel out, and it works out to be 1.066 mole. So 1.066 times the number of, times Avogadro's number would give us the exact number of helium molecules. The second part of the question, so we can just leave it right there. We can just say 1.066 moles. That's how many helium molecules we have. Now, the reason I've included this, I've cut and pasted from the periodic table, helium's entry that has its atomic weight here. So the way that moles relate to atomic mass is this is how much in grams 1 mole of helium will weigh. So if I have 1.066 moles of helium, the mass is going to be, and I really only need 3 significant figures there, 4.00 grams per mole multiplied by 1.066 moles of molecules. That gives me 4.26 grams. That's the mass of the helium inside this balloon. So how many molecules? That's answered right here, 1.066 moles. And what's the mass? 4.26 grams.